So differential equations really is a natural extension of everything you learn in calculus. Differential equations is really where the ideas of calculus are put to the test. It's where they're most often used. So we want to do a quick 5-minute review of the basic concepts of calculus. So the whole context of calculus is that you have something, some quantity, some number that's changing over time. Now time would be our independent variable, and y, whatever it is, would be the dependent variable. It depends on time. Now this could be a motion problem. It could be an object that's moving, so the quantity that's changing over time is the location. Or it could be an amount of money in an account that's changing over time. Or it could be the temperature of some water that you're heating up. That would be changing over time. Okay, so sometimes we write just plain old y, or of course we could use other letters. For temperature we might use capital T. For a motion problem we might use D for distance or H for height. Of course the letter doesn't matter. Sometimes to indicate that it is changing over time, that it depends on time, we will write y of t, right? And of course that means that we can specify what y actually is at different times, like y in the beginning maybe is 36.2, and then maybe y 1 time unit later is 38.9 or something like that. And I'm talking generally here, so I don't have any units. Depends on what y would be. Those could be dollars, those could be meters, those could be degrees Fahrenheit. Okay, now here's sort of a really important fact that it's always important to keep in mind whenever you're dealing with a quantity that changes over time. How do you describe a quantity that changes over time? And there are 3 ways to do it. Number 1 is qualitative. Now that actually that's really 2 ways in one. Qualitative just in general means describing it without getting too numerically specific, without getting into details with the numbers. So that might be just simply words. Like you might just describe that y increases but levels off at 40. Something really basic like that. So that's qualitative. It's not quantitative. That's not telling you exactly what y is at any time, of course. It's really, in fact, that's sort of the vaguest thing you could do is say something like that. It increases and then levels off at 40. But it's something. It gives you some sense of the behavior. The other half of qualitative would be, and this is hugely important, a graph. You can graphically describe it. So some quantity that increases but levels off at 40 might go like that, right? So that's still not numerically precise. Like we might be able to eyeball it, but we don't really know what y is exactly at any given time. We could, if depending on how accurate the graph is, we can estimate pretty well from the graph, but it's still not being quantitatively precise. So words and graph, that's the qualitative approach to describing a quantity. Now the second way is numerically. Numerically is quantitatively precise, as you might guess, and usually that would be expressed in some sort of table. So it's just simply a list of numbers at different times and what y is at those times. So that would be a numerical description of the quantity. Now this is precise in that you know what y is at specific times. Of course, it's still not the best possible situation because you don't know what y is at the in-between times. You don't know what y is before the beginning of the table or after the end of the table. Every table, of course, would only have a finite number of numbers in it. So for the ones that are there, that's very precise, but it's not complete information. And then finally, the third way to describe a quantity that changes over time is what our text calls analytic. What we mean by that is a formula. So there'd be some formula that would depend on time, and you could just plug time in and that would tell you what y is at any given moment. So analytic, or a formula description. Now, the important thing to understand is that not every quantity that changes over time has a formula. So this is only, if you're lucky, one of these exists. You can always graph any quantity, and you can always make a table of numbers for any quantity. You can't always make a formula that matches any quantity. Only some really specific things follow formulas, right? If you go ride a bike, your distance from where you started is almost certainly not going to follow a formula. Now, sometimes you can maybe get a formula that is close, but nobody rides a bike precisely according to a formula. The money in your bank account probably doesn't follow a formula if you're making deposits and withdrawals at random times. Now, if you just leave it in there and let compound interest do its thing, then it would follow a formula, the compound interest formula. So again, sometimes you have a formula that applies, sometimes you do not. If you do have a formula that applies, that is the best situation, right? Because now that's better than a table. You can plug any number in and get an answer, and it's numerically precise. And by the way, also, if you have a formula, of course, you can use it to generate a graph. And then, of course, you can then describe that in words. So in Analytic, if you have a formula, you kind of have the whole package. Okay. Now, again, I just want to emphasize that these three approaches to describing a quantity are of the utmost importance. When we're working with differential equations, we're going to be trying to get a handle on what the quantity is. And that's a vague question, what the quantity is. The way we're going to answer that is going to be in one or more of these three ways. We're either going to be able to get a formula for it, that would be the best, or we might just generate a list of numbers and not get a formula, that would be almost as good. Or maybe we'll settle for just some qualitative information. We'll just sort of roughly describe what it does over time and maybe get a rough graph for it as well. So in most of the problems we do throughout the semester in differential equations, the answer will be one of these three things, because we're always going to be looking to describe some quantity y, and depending on what we have to work with, we're going to do one of these three things. Now, to calculus, right? The central idea in calculus is the idea of a derivative. So you have this quantity that's changing over time. So what that means is that at every moment in time, there's actually two things. There's what y is itself, right? There's, what y is at time 0 and what y is at time, 0.6. At any moment in time, you can say what y is. The second thing is you can also say at any moment how fast it is changing, right? Y is changing. So that's the derivative. How fast y is changing. It is the rate of the change of y. And there's two notations for this. There's the English way of writing it, which is y prime. Again, you can put a parentheses t next to it if you like. Or there's the German way of writing it, the continental way of writing it, which is dy over dt. Now, our book actually uses this version more than the first version. Usually in Calc 1 you learn this one, you use that one more. Hopefully you've seen both. But either y prime or dy dt are the two ways of writing the derivative. And again, that's a rate of change. That's how fast y is changing. And so if that number at any given time is positive, it means that y is growing at that moment. If the derivative is negative, it means that y is going down, it's decreasing at that moment. The bigger the derivative is, means it's changing faster. And the other thing to realize is that it's also changing all the time. How fast y is changing itself is probably changing. Really simple situations, you might have a quantity y that's changing at a constant rate. That would just be a linear formula. But in general, usually most things change at a changing rate. So the rate itself is changing. So there's a different value for the derivative at every moment. Okay. Now, when you're talking, we're going to get into those three ways of describing a quantity, right? And see what the derivative looks like in each of those. So first of all, numerically, what is the derivative? Well, if you have your formula sort of in a numerical sense, where you can say what it is at different, you have the number at different times, then the derivative is this. It's at the moment you're looking at, you look at the change in y, how much y is changing over a very small time interval. And now to make it a rate, you divide by the change in time. You divide by the size of the time interval. Now usually what we do, instead of writing that out in words, is we use the delta notation, which you may be familiar with. Delta in math just means change in. So we want delta y divided by delta t. So in other words, if you wanted to know the derivative of y at time 4.5, say, then what you would do is you would see what y is at 4.5. Say it's 26.832. And then you would look at what it is at maybe 4.51, just a little bit later. And maybe it's 26.839. Okay. And so then you would compute this. How much did y change by when it went from here to here? It changed by 0.007. And how much time elapsed? How much did t change by? It changed by 0.01. And so I think we get 0.7 there. Okay. So, and that would be an approximation for how fast y is changing at 4.5. Now, a little bit of a technical thing, an important technical thing. I said approximation, and that's right. And actually, I've written this incorrectly. This should be approximately equal to. Because what we did not do is figure out how fast it's changing at 4.5. What we just did is figure out how fast it's changing on average over the span from 4.5 to 4.51. Now that's such a small time interval that probably is very close to the instantaneous rate of change at 4.5, but technically speaking it's not exactly right. Now what you should do really is, instead of doing 4.51, you could maybe do 4.501 and then do 4.5001 and so on, and get closer and closer to the 4.5. Make your time interval, your delta t, smaller and smaller. And so of course the way we write that is dy dt actually is equal to the change in y over the change in t in the limit as the change in t gets smaller and smaller and goes to 0. So what this number gets closer and closer and closer to as you make your delta t smaller and smaller, that's the actual derivative at 4.5. Okay, second, what is the derivative graphically? You can say that in one word, right? Slope. If you have y as a graph and you want to know what the derivative is at any moment in time, the answer is it's the actual slope of the curve at that point. It's the slope of the tangent line, the line that sort of is the straight line version of that curve right at that point. Slope, you remember from high school algebra, is rise over run. Your run is obviously a change in the y-coordinate. Your rise is a change in the y-coordinate. Your run is a change in the t-coordinate. And so actually you see that rise over run really is just this computation. It's the change in y over the change in t. But again, graphically, the interpretation is it's the slope. It's how steep your graph is. So that's going to be a really important fact. It was important in calculus, right? And it's going to be really important in differential equations. And then finally, the formula approach, the analytic approach. If you actually have a formula for y, then almost certainly you can get the formula for the derivative, which is, really, really great. And so now, of course, that's what a lot of Calc 1 is about, is learning all the rules for turning formulas for y into formulas for the derivative of y. And so what you'll want to do is just make sure you're sort of okay on those rules and remind yourself how those work. Of utmost importance would be the derivative of any power. So I'll use the prime notation to write these rules. t to any power, right? The derivative is you bring the power down and then you knock it down by 1. Okay. Another really important rule is the exponential rule. The derivative of e to the t is itself. The derivative of the sine function is cosine. The derivative of the cosine function is negative sine. And the derivative of natural log is 1 over t. Okay, so these are some of the derivative formulas for the basic formulas that make up a lot of the formulas that we will encounter. Now there's more, of course. There's more trig functions, there's inverse trig functions, and there's other things, but those are the basic ones. Now, the average formula, though, is not just a single one of these, but usually made up in some sort of combination of those. And so then you'll also want to remember the product rule for when you have two of these multiplied. You'll want the quotient rule. And of course, the most important one, the chain rule, which is when you have one of these formulas inside another, and how you take the derivative of that. What I didn't write down is the addition rule, or the sum rule, which just says that if you have two of these guys added together, you just take the derivative of each one and add them together. Most people don't even think of that as a rule when they do it. The other one that's like that is the constant multiple rule. If you have 5t squared, you take the derivative of the t squared and you just keep the 5 along with it. So it would just be 5 times 2t. So constant multiple rule, again, most people don't think of that as some official rule. It's just so natural. But product rule, quotient rule, and chain rule, right, those you do have to be sort of conscious of when you're using them. Okay, so yes, you'll want to review these rules and make sure that you're okay with taking derivatives of formulas. And in general, you want to make sure that you're okay with the concept of a derivative numerically, graphically, and as a formula.